Okay.
Oh, don't forget to record it, yeah?
Yeah.
Yeah.
So now I have to share screen and, okay. So let's talk about some supplementary ideas to the previous lecture. We saw last time, we reminded everyone what a bounded symmetric domain is, and we saw that the velocity addition introduces affine automorphisms of the velocity ball, and the velocity ball is a bounded symmetric domain with respect to this group of automorphisms. Then we computed the generators, the Lie algebra of this group. The group is made up from the velocity addition, so the generators generate changes in velocity, which we can think of as accelerations. And then we could have continued and gotten the dynamics equations, but we took a detour, and instead of continuing with the 3D, we went ahead and looked at a 4D formulation. And so we defined the basic definitions in four-dimensional Minkowski space-time. 4 vectors, the light cone, we defined the 4 velocity, the 4 momentum, the 4 acceleration, the 4D version of everything. And we saw a basis with 6 elements of the Lorentz group, 3 for the boosts and 3 for rotations. And then we saw the 3D dynamics equation, which is not Lorentz covariant. And we showed that there's a 4-dimensional equation, which we'll get in more detail in a minute, a 4D equation, dynamics equation, which extends the 3D and is covariant. Here's a short summary of what we saw with the affine automorphisms. So you can see the action here on the ball. These slices are supposed to be edge on and are shown slightly bent for effect. And each slice gets moved to the right if the boost velocity is in the x-axis. And you can see in the right-hand picture how the velocities are affected by these boosts. And notice that lines go to lines. This is the projective geometry. Lines are preserved, but angles are not. And then we calculated the generators, or showed what the generators are, by differentiating smooth curves in this group of automorphisms. This led to a dynamics equation. Pictures of the corresponding vector fields, one for a boost, the left-hand side is for a boost, and the right hand for a rotation.
No, boost and rotation.
Yes. The left is a boost, no?
This is the boost, and this is boost and rotation together.
Ah.
Because you have an acceleration here and a rotating here.
Okay. Now, getting back to the point of embedding the 3D into the 4D, we saw that the 4 acceleration in relativity depends on the 4 velocity, not like in classical mechanics. And we assumed that this dependence is linear. This led to a 4-dimensional dynamics equation where the acceleration A is the product of a 4x4 antisymmetric tensor A times the 4 velocity U. Showed how the 3D equation is really a part of this 4D equation. So in this equation, which is 4D, you have just the 3-dimensional force. This would correspond, for example, to when there is only an electric field and no magnetic field. But if you Lorentz transform to another inertial frame, a magnetic field will pop up. So for example, let's take electric field in the x direction. So the generator would look like this in the antisymmetric form, 1 and -1. This is the direction of the electric field, so it's in the x. And the 3x3 zeros on the bottom mean there's no magnetic part. And if you want to use this as an operator, you have to raise one of the indices. So the -1 becomes a 1. And I want to introduce some notation just by the way that Yaku's going to need for his part. E01, where's my mouse? E01 means a 4x4 matrix with a 1 in the 0 row in the first column and zeros everywhere else. So that would be a matrix with zeros everywhere except a 1 here. And E10 has a 1 in the 0 in the first row 0 column and zeros everywhere else. So it's a way to break down the matrices. So let's take a Lorentz transform to a frame K prime who is moving in the y direction with velocity v with respect to k. So the electric field in k is in the x direction, and now we're going to travel in the y direction. And using, these are the Lorentz transformations, forward and backwards, from k to k prime and k prime to k. And when you transform the antisymmetric tensor to the frame K prime, now you'll pick up a magnetic part. Before the bottom right 3x3 was all zeros, now you pick up a magnetic part pointing in the z direction, which corresponds to a rotation in the xy plane. So in K prime, he'll see the field as having both an electric and a magnetic component. And since the field is in the x direction and your relative velocity is in the y direction, the magnetic part is, corresponds to a rotation in the xy plane. Okay, the next thing I want to talk about is the symmetric velocity, because we're going to end up repeating the same process which we did for regular velocity addition for symmetric velocity addition. So again, the symmetric velocity, if the velocity between the two moving frames there is v, then the velocity with respect to the small frame in the middle is the symmetric velocity w1. We prefer to use a unit-free velocity. We call it S velocity. We just divide the regular symmetric velocity by c, all of S velocities. The regular velocities and symmetric velocities are in one-to-one correspondence. You can always transfer back and forth. If you have a regular velocity v, you can turn it into an S velocity with this formula. And if you have an S velocity, you can easily go back to the regular velocity with this formula. How we define the addition of S velocities. Two S velocities, A and W, and you want to add them together relativistically. So you pull each one back into a regular velocity using phi. So phi of A and phi and W are the corresponding regular velocities. You add them together by Einstein velocity addition. Gives you another regular velocity, and then you pull it back with phi inverse and turn it into the corresponding S velocity. That's the physical definition. Take the calculations to come up with this complicated formula, but you'll notice that the sum of A and W is in the plane spanned by A and W. It's some number times A. It's a linear combination of A and W. So you can work only in the plane. You can complexify this plane. And using the substitution, A dot W goes to this, and W squared is WW bar. So the velocity addition formula becomes much simpler. It's analytic in W, and it's one form of the Möbius transformation. And it turns out that the symmetric velocity addition is a conformal automorphism of the symmetric velocity ball. And together the rotations form a group of automorphisms of the symmetric velocity ball. And this ball is also a bounded symmetric domain with respect to this group. And here's a picture of how the velocities change under the symmetric velocity addition. In this case, angles are preserved, but lines are not preserved. The projective geometry where lines are preserved, but not angles. And as before, we can compute the Lie algebra of generators. which turn out to be, as shown here, where this triple product is defined as follows. And it leads to a dynamics equation for the S velocity W. The equation is analytic in one complex variable, which means you can get analytic solutions. From where does the analyticity come? If you look at the generator of a boost, just pretend that capital B is 0. So this is the generator of a boost. You write down what the definition of the triple product is, and the W bar term cancels out, and you're left with an expression which is analytic in W. If we had tried the same trick of complexification with the projective geometry, where the generator of a boost was this one, A minus Z dot A Z, it won't help you to get analytic because you'll still have a Z bar term. So you get the analyticity only with the conformal geometry. Okay, and finally, a nice exercise just to help you get a feel for what a non-positive definite metric is, since we can have negative lengths. What does it mean to have a negative length? So if you have two events, the coordinates measured in some inertial frame K, and it turns out the difference between these events, these two events is negative, it means that there is an inertial frame in which these events are simultaneous. So the proof is, let's do the backwards direction first. If they're simultaneous in some frame K prime, the zero component is the same. So when you compute the metric, you'll get 0 and then the minus part. So obviously the interval is negative. And since the metric is invariant, this interval is negative in every inertial frame, including K. The other direction is a little more interesting. If the interval is less than 0, by making a rotation if necessary, that x2 equals y2 and x3 equals y3, and which means that the difference in time component minus the squared minus the difference in spatial component squared is negative. So now you want to find a Lorentz transformation to a frame K prime in which the events will be simultaneous, which means you want CT prime to be 0. Oops. The presentation disappeared.
Okay.
Okay, here it is. So you want the CT prime to be 0. So you plug in the vector, the difference of the two events, and you set the time part to 0, and you apply this Lorentz transformation, and it turns out you would have to take a velocity v equal to this one, which, because this is negative, so x0 minus y0 is less than x1 minus y1, and therefore you get a velocity less than c. So there is a velocity which leads you to a frame where the events are simultaneous. Okay. Thank you. Now I'm gonna stop recording.
No, I can stop on it.